Thank you, and welcome to the Center of Urban Horticulture, which is part of the School of Environmental and Forest Sciences of the College of the Environment of University of Washington. I'm really personally interested in the particular topic today for a whole number of reasons, and I'm interested in it from the standpoint that a lot of my academic life has been about carbon exchange and the role that different kinds of plant and tree stresses have on that exchange. But I'm also, as a person who's been leading a field trip course for the last almost 14 years, interested in the sort of condition of forests. And I'm interested in our thought processes as we think about different elements that we might put into the tool bag that one uses in stewarding forests, in keeping forests either in their various different kinds of ownership, including private ownership and private use. And I see today's conversation being really important as we talk about the carbon cycle and we talk about the health of forests and how these things all may interplay as we move forward into in the next time period. There's been what I regard an interesting anthropogenic convergence on our forest systems. Washington State is blessed with about 50% forest cover that's managed by a whole range of different jurisdictions, agencies, and people. And we find ourselves in a discussion about the role of forest health or forest condition, forest resilience, renewable energy, socioeconomic benefits that can be derived from the forest, particularly in rural communities or in rural parts of the state. The role that altered climate, whether it's weather extremes, El Nino, La Nina cycles, or climate change, altered disturbance regimes, invasive organisms, including disease organisms and plants and animals, and then the whole aspect of multiple stakeholders. And there is, I think, the emerging realization that doing nothing has significant consequences on forest condition. And I would opt that doing nothing is not an option. So I see the discussion about carbon cycling and how forests are tended or stewarded in the future as being an integral part of the discussion that's being carried on today. I'm going to introduce Ellen Matheny at this point, who is actually going to introduce all the speakers and coordinate the rest of this program this afternoon.
Tom Gower is a professor of forest ecosystems ecology at the University of Wisconsin in Madison, Wisconsin. Professor Gower's research interests revolve around forest carbon. He holds a PhD in forest ecology from the University of Washington, a Master of Science in forest ecology and soil science from North Carolina State University. Please welcome Professor Tom Gower.
So I'm going to briefly touch on sort of 4 topics. I'm going to do a little brief overview of how I view systems ecology, particularly the biological ecosystem and the industrial ecosystem and carbon management objectives. And then I'll talk a little bit about biological ecosystem carbon dynamics, really focusing on the energetics of forest ecosystems as they go through stand development. And there's some pretty unique opportunities there that affect the way we can potentially manage forests for carbon management opportunities. I'll finish up talking about the industrial ecosystem dynamics, a study that I did with 4 collaborators, Home Depot, Storenso, Time Inc., and Cam4. And then I'll have a few concluding thoughts, not a lot of answers, probably more questions than answers. So that's what we'll talk about today. So this is my cartoon version of how I view the world. At the top, that's the forest system cycle, or the forest system ecosystem. It's comprised of 2 sub-ecosystems, the biological ecosystem and the industrial ecosystem. And as far as the biological ecosystem, the plants take up carbon or carbon dioxide from the atmosphere. Some of that's respired back into the atmosphere. But the net difference between that gross primary production and autotrophic respiration is net primary production. So that's the organic matter that's stored in the above and below ground vegetation. Then the other primary loss of carbon dioxide from these forests is the heterotrophic respiration, that RH at the bottom there coming out of the soil. And that's the CO2 that's released as decomposers, fungi, bacteria start breaking down soil organic matter. And so the difference between this net primary production and the heterotrophic respiration is referred to as net ecosystem production. So the nomenclature that I'm using as opposed to atmospheric chemist is when a value is positive, an NEP value is positive, it means that the forest or any terrestrial ecosystem is actually absorbing CO2 from the atmosphere or helping to offset atmospheric CO2 concentrations. If it's negative, that means it's a source and releasing more CO2 to the atmosphere than it is absorbing. If you sum NEP across a landscape, so you can imagine a landscape of various different stand ages or disturbance regimes, we use a term called net biome production, and that's simply the sum of NEP across these patchwork of forest types, forest age classes, and histories across a landscape. Now, the connection between the biological ecosystem and the industrial ecosystem is the harvesting of material from the forest, and then it is transported into this industrial ecosystem where it undergoes a number of processes. So we have emissions associated with the management and harvest of the forest. We have emissions of transporting that fiber from the field to the primary, secondary, and tertiary processing facilities. And finally, the transportation of this finished product to the consumer and then its final fate. And so what I'll try to do today is walk through and give you a couple of examples of each of these where I perceive there be some significant opportunities to manage carbon in a sustainable way, but I'll also point out there's decisions that we have to make about what our actual goals are. So, all right, so this is a very famous conceptual model. It was probably first originally proposed by Odom, at least part of this. On the x-axis we have time, and on the y-axis we have carbon balance. Okay, so again, if it's positive, the forest is growing. If it's negative, there's carbon that's being released. So there's three curves there. So this net primary production curve is saying how the growth of that forest changes over time. And so you can imagine after a stand-killing disturbance, there's no vegetation there in extreme case, so NEP is 0. As revegetation starts occurring, NPP goes up and comes down. But on the other side of the coin, when you remove the vegetation, the soil is warmer, it's perhaps more moist, and so you get increased decomposition. So that RH, or the red curve, is the CO2 that's released to the atmosphere from decomposition of organic matter. The blue curve is the balance between those. And so that's telling you whether that system is a carbon sink or a carbon source. So early on in disturbance, I think Sprugel first hypothesized that the forest is a carbon source. You have no NPP, and yet you still have decomposition occurring. And you can see how it changes midway through succession. NEP is a maximum, and then it reaches some equilibrium. Well, there was an interesting paper that came out in Nature in '08 by Lucert and some others, and they claim that the old-growth forests are actually carbon sinks. So if they were to redraw this diagram, that blue line would be squiggling around somewhere above that 0 line. So that was really a very different finding than some of these early conceptual models. So I recently compiled data from these NEP measurements for forests of similar type. They only differed in the age since last disturbance. And so we refer to this sort of chronosequence of this group of stands that only differ in age. And what you can see, the early young or short-lived species, jack pine, black spruce, and black spruce in Quebec and Manitoba, they all exhibit that same curve, that hypothetical curve of this initial loss in carbon following catastrophic stand disturbance. They reach a peak and then drop off somewhere around 0. The more long-lived species, and one of them didn't show up, it looks like, northern hardwoods is in orange, Douglas fir is in the black X's out there. They also exhibit this same pattern of large carbon loss, following catastrophic stand disturbance, reach a maximum, and again, much longer in life, they come out there and sit somewhere around 0. So this is a very different finding from the Lucert paper, but the key thing to recognize here is that you have these 4 very distinct stages in stand development, and they have important implications for carbon dynamics. So this graph simply is taking an average of those multi-year measurements of NEP at these old growth stands. 3 of the 5 are not significantly different from 0. So that suggests that those old growth forests, the black spruce in Manitoba, the northern hardwoods forest in Wisconsin, and the Douglas fir forest in Washington, Pacific Northwest, basically have an NEP of 0. They're carbon neutral. 2 of the other sites, the Corona sequences of black spruce in Quebec and the jack pine in Saskatchewan, are slightly significantly different or greater than 0, but those values you can still see are far less than the 2.6 that was reported in that literature review. So with that information, it gives us some insight into carbon dynamics as forests recover following disturbance. And I'm going to switch gears and talk primarily about northern Wisconsin forests now. During the late 1800s, early 1900s, that area was basically entirely clear-cut from these historic photos you can see here. And so this provides, or forest ecosystem models provide a way to evaluate or understand how historic land use affects carbon dynamics, and also a tool to project into the future of how carbon dynamics might be affected. So my little playground is the Chequamegon-Nicolet National Forest up in northern Wisconsin. It's a fairly large forest, produces a large amount of timber. Actually, it typically ranks 3rd or 5th somewhere of all national forests. So this is a diagram that we use or we built from a simulation of a forest ecosystem process model. On the x-axis you have time, and on the y-axis you have net bound production on the y-axis, and on the far side you have total harvest. So that gray histogram on the bottom is the amount of wood that was harvested over time from that Chequamegon-Nicolet National Forest. And what you see is as the harvest started increasing, the net biome production, or the carbon exchange between the forest and the atmosphere, went negative. So those forests were releasing carbon to the atmosphere. Then, as harvesting, the initial phase of harvesting subsided, you see net biome reaches a maximum in the 50s and 60s as we started getting vigorous regrowing forests. And now we seem to be on the down slope of that again, where the carbon sequestration potential is actually decreasing. So we took our model, and instead of running it for this large landscape, we played a sort of a what-if scenario game and said, well, what happens if we do different harvesting regimes? So I've got 3 panels. We'll focus on the vegetation carbon content, so that's just the amount of carbon that's in the vegetation on the top, and the bottom panel is how much carbon is sequestered annually. And you can see that the harvesting regime has a big impact. If you want to manage for carbon content, carbon storage, no harvest seems to be the way to go. On the other hand, if you feel that the management objectives should be maximum sequestration, then no harvesting actually results in less carbon sequestration, and these infrequent selective harvest results in greater sequestration, at least for our northern hardwood ecosystems. So we ask, the next question is, how do we optimize? If we want to say optimize for net ecosystem production, so the maximum ability of these forests to sequester carbon, then what do? If you can see the red line, so we have time on one of the axes, percent harvest on the axis sort of running out that way, and net biome production on the z-axis. The red line is the current harvesting rate that's occurring, which is actually only half of the allowable cut. So there's where Chequamegon-Nicolet currently operates. And our optimization analysis suggests, you really want to be up where that light green area is. And if we were to increase harvest by 2.5% of the area, we could increase the carbon sequestration capacity of this forest by 30%. So you're basically shifting the age structure to that more younger age classes that have a higher sequestration potential, if that is your sole objective. And that's an important point to make. So, point here is stand structure, age class of the stand has a very pronounced impact on carbon sequestration. This is a diagram from a life cycle that I did for dimensional lumber and Time in-style magazines. I throw it up here because it's complex, and this is a cardinal rule, you don't use complex graphs, but it makes my point that these life cycle inventory studies are extremely complex. That's why we don't have enough of them to understand our carbon footprint of our wood and paper products. So that's really all I'm trying to show here. And I just want to move on to the meat of that study. And we found that for Time and In-Style magazines, we released about 1.2 tons of CO2 equivalent, so that's CO2 plus methane and NOx, per ton of magazine produced. For dimensional lumber, it released about 0.8 tons of CO2 equivalents per ton of dimensional lumber. And you can see on the bottom section there, I've broken the emissions down by each process. So H stands for harvest, transport to the mill emissions, and you can sort of read the rest. So you can see the relative contribution of emissions differs dramatically from these two products. With paper or magazines, the biggest emission is coming from the mill. Thermomechanical processing is extremely energy intensive. On the other hand, the dimensional lumber, the big emission comes from the transport to the consumer. That's way different than any study you'll ever find. And the point that I wanted to make with this graph, and you may not be able to see it, if you can see every state or province that's in gray, that province or state is getting dimensional lumber that was made in northern British Columbia. So you have these enormous transportation chains that are contributing to large emission losses. Is that sustainable? The story on the magazine side of things is, so Time Inc., which is one of the largest publishers of magazines in the U.S. and probably the world, so if these numbers are representative of other magazines, it gives you some idea of what's going on. So they make about 37.5 tons of magazines a year, at least for Time, and we followed the emissions both for the newsstand as well as the subscription. Look down below the newsstand. About 2/3 of the magazines that go to the newsstand are never sold. Huge inefficiency. And then if I hit the button, another red circle should have appeared. Look at under the subscription side of things, the large percentage of magazines that are never recovered. So we don't quite know whether they're probably not recycled, they're probably being landfilled or incinerated or whatever. So the point here is there's tremendous opportunities, at least in the magazine industry, to change their footprint quite dramatically. And so if you reduce the consumption or the inefficiencies in both of these industrial ecosystems, you require less fiber coming from the forest, and maybe that gives us more fiber or greater protection for primary forest or greater fiber for bioenergy. So the point here is that the two are intimately coupled. Okay, general conclusions. I think based on our study, I think it's a little dangerous to say that all forests are carbon sinks, at least the ones that we study. They're not all carbon sinks. Probably the second important point I'd like to make is the carbon management opportunities depend on a lot of things. And the results I showed you probably are very unique to northern Wisconsin and the Lake States, given their very unique stand history. We also need to decide whether your objective is carbon storage or carbon sequestration. Those two objectives take you in very different directions. Also, we need to think about the appropriate silviculture and risk for each biome. If it's carbon storage in a fire-prone area, that may not be the smartest carbon management strategy because it could conceivably be destroyed in wildfire. Some systems are receptive to selective harvest, others are not. As far as industrial ecosystems, wood and paper products contain carbon, but they are not effective carbon sinks if you include the whole story, all the emissions that are released to actually make the material and transport it to the consumer. So I think that's an extremely important point. And I also will admit that that CAM4 project that you saw, I think it is an extreme example. I have never seen emissions related to transportation that high. So it just goes to show you what can happen when you get long transportation chains. Many opportunities to reduce carbon emissions, and then lastly, the whole ecosystem. What we now need, in my opinion, is optimization analysis for multiple ecosystem services. Carbon sequestration is not the only thing that we need to be thinking about. We've got biodiversity, water protection, soil protection, et cetera, et cetera. Thank you.
Our next speaker is Elaine Oneil. She is a research scientist in the School of Environmental and Forest Sciences at the University of Washington, and also the executive director of the Consortium for Research on Renewable Industrial Materials. She holds a PhD in forestry from the University of Washington, complemented with years of experience in forest management. Please welcome Dr. Elaine Oneil.
I wanted to start with this particular chart, which I think most everyone has seen. It's the atmospheric carbon dioxide concentrations that have been increasing since 1960. So you see the trend line going from below 320 to almost 400. And then you see the little squiggle. That's the northern hemisphere's forest breathing in and breathing out twice a year when we put on leaf and then we lose leaf during the winter. And that becomes part of the story as we go along. So when you look at that concentration, and there's a concern about climate change and increasing CO2 in the atmosphere, you have to think about where can we start to remove, how can we remove that excessive CO2 from the atmosphere and perhaps mitigate some of the climate change impacts that we are seeing currently in this part of the country. And so if you think about it, there's some 4 major sinks and sources of CO2 to the atmosphere. You have the oceans and the atmosphere. There's an exchange there. There's a two-way flow of carbon dioxide between the ocean and the atmosphere. There's the same that Tom went into in detail between the forests and the atmosphere. There's a two-way flow there. Between the land and the atmosphere, there's a two-way flow there also. But when you look at the fossil fuel reserve in anything but geologic time, we're basically looking at a one-way flow of CO2 into the atmosphere in terms of our burning carbon-based fuels, fossil fuels, to produce our energy. Now, granted that CO2 is taken up by the other sinks in this system, but the question is how much, and how much can those sinks do relative to the amount that's being pumped into the atmosphere. If we look at this, I borrowed this one from the Woods Hole Research Center. They did a very good job at looking and identifying the 1,000-pound gorilla in the room, and that is our fossil fuel use. If you look at that chart, time is on the x-axis, and here's your annual flux, your emissions to the atmosphere. And what you see in the red there is that your fossil fuel is really driving this increase in atmospheric CO2. There is also a little bump up from 1960 onward in what they call land use. So that's your emissions from land use change, deforestation, and the like. Most of that being deforestation in the tropics. In North America, you don't actually, in fact, we have an opposite sign in terms of the amount of carbon dioxide that's been sequestered in our forests since 1960. These charts come from a U.S. Forest Service publication in 2009, and you have 4 regions. You have the north, the south, the interior west, and the Pacific Northwest. Your green bars is the amount of what they call growing stock that's available through time, and then your red is your harvest, and your yellow is your mortality through time from 1953 to 2007. So in each one of these regions, we're actually seeing an increase in the amount of growth or the amount of forests in the U.S. relative to that bump up from land use and land use change. So whatever the U.S. is doing, they're not contributing to that particular problem on a large scale. Can we continue this particular approach of continuing to absorb all of the fossil fuel emissions and use forests as that system? Well, there might be some regions that you can do that, but there's a lot of regions, in particular in the western US, where that's probably not the case. We have in the western US, actually western North America, a really significant climate-induced insect and disease problem. 35 million acres in British Columbia are dead from mountain pine beetle. Not all of them look this bad, but most of them do. There's another 41.7 million acres in the western US. That's cumulative from 97 to 2009. That comes from a Western Bark Beetle Initiative study. Now, that's not just a single bark beetle. That's 21 different species of beetles. So if you add those numbers together, that's more than 3 times the amount of forest that exists in this state alone that has been essentially removed in terms of its ability to continue to sequester carbon, at least in the near term, until you go through that decay function. So in that particular instance, we're looking at least one region in the US where we're probably not going to see that increase in trajectory, and we need to think about what the implications are in the long term for that kind of condition. Now, the next thing about those kinds of bark beetle outbreaks is that if there is, they tend to make extremely good firewood. If there is a lightning streak or a careless camper in a region like that, you get a wildfire that's essentially uncontrollable. Here's a particular example from 2006. It's a tripod complex. That's the smoke plume from that fire. It basically consumed an area that had been in the prior 5 years almost completely, most of the pine component was completely missing because of mountain pine beetle epidemic. That's about 1 million SUVs running for a year from those emissions, the initial emissions. That didn't actually count the methane, so it's probably higher than that. So we're looking at both a loss of the ability to sequester and absorb, and then these releases that have to be accounted for in the whole carbon cycle. So if you step back from that, you start to look at what are the implications for being able to use our forests as storage vehicles, and there's certainly some regions where that's obviously not the case. The other element that emerges when you start looking at those kind of things beyond the near-term consequences to air quality is the fact that in some of these conditions, when you have severe wildfire, you can have a substantial loss in your soil carbon, and you can also have a substantial chance for regeneration failure. Now, if it's a managed forest, typically they're salvaged, the money is used to reforest, and you can continue to start to sequester. If we're dealing with unmanaged forests where there's really not enough funding to go in and regenerate, and we're relying on natural regeneration, there is certainly a shortfall there that's starting to emerge in the western forest just from lack of funding. So if we go back to these major sinks and we start to look again at what is the role of forestry in this carbon economy, we have this ability to look at the forest as a storage vehicle, but we also have to have the ability to look at it as a replacement for those fossil fuels, to take on the 1,000-pound gorilla, as it will, by looking at how forests, what is the ratio of, what's the ability of forests to produce building products and fuels, and in producing them, actually reducing our reliance on the fossil fuels that are creating the problem here. In order to do that, to understand your trade-offs, to understand the implications, you need to use life cycle assessment. For the past almost 15 years now, the Consortium for Research on Renewable Industrial Materials has been doing just that, looking at all of the major wood products in the US to come up with essentially their life cycle inventory and assessment, their carbon footprint, and a whole lot of other footprints, but specifically focused on carbon in this particular presentation. Here's a subset of some of the products that we've looked at. So there's oriented strand board plywood, laminated veneer lumber, glulam, and 2 kinds of lumber. Take-home message, this is your total energy per cubic meter to produce. The take-home message is we can get to this number. It's fairly obvious. We know what the the big drivers are in the mill. We know where the harvesting is. We know what the transportation costs are. Now, this is local, not your Chetwynd to Timbuktu average. And so that starts to provide us with some information that we can then take forward and say, if we're going to use wood in the place of products that are very fossil fuel intensive to produce, like steel and concrete, what are our trade-offs? Where is the biggest bang for the buck? So if you start making the comparison here, this is carbon dioxide in kilograms per cubic meter of wood equivalent. Takes so much concrete to make a floor area versus oriented strand board or plywood or kiln-dried lumber, and you start to see that in terms of fossil emissions, which are in the red, there's a huge disparity between wood products and these other products that we use in buildings. The other element in wood, which we're still in discussions on, is the fact that a good portion of the energy used to produce wood products actually comes from burning the residues. Anymore, we use virtually 100% of the log that makes to the mill. Whether we're using it as hog fuel or we're using it as a chip, or even if we're using it as beauty bark, virtually 100% of that log is used. So if you back out what we're calling the carbon neutral biofuel, you'll see a different sort of picture, which is in red, but this doesn't account for the carbon that's actually stored in the wood product. When you measure the amount of carbon that's sequestered for the life of that product in the product, you see that in all of these cases, the wood product is actually a net storer of carbon, just like the standing forest is storing carbon for the life of the forest or the life of the product. That gives us the ability to start to put together, compare products that are comparable. So if you're going to put in a beam, it can be out of steel or it can be out of concrete or it can be out of an engineered wood product. You can start to make those comparisons and see where your best trade-offs here. Here in all cases, when you focus more on wood, on the wood side versus the fossil fuel intensive side, you'll see that typically you're able to store more carbon in the building than it took to actually make those products. Here's another way of looking at it, and I'm putting this in because of where we're going here. This is the kilograms of CO2 reduced per kilogram of wood fiber used. In this case, there's a couple of things to point out. One is that using wood for fuel actually gives you less of a benefit than if you're using it to replace a steel beam, the one in the middle. That's almost at 10 kilograms of CO2 reduced per kilogram of wood fiber. That's a huge leverage. And so the story that I carry when I talk to engineers and architects is we need to find a way to use wood in those applications. And there are people that are really coming up with some amazing design potentials to use wood in ways that we haven't typically thought of it before. Here's one example. This is a high-rise in the center of London. It's 9 stories. At the time it was built, it was the tallest wood building ever built. It's made out of something called cross-laminated timber. For every kind of application. It's for the beams, all the supports, the slabs. They even used it in the elevator shaft. This is making people very excited. That takes us back to this growth chart. So here's our growth over time in Pacific Northwest. And then when you harvest, you have a product. We know from our life cycle how much of that product goes into wood building products versus is burned for biofuel versus is left to decay in the woods. Below the line is our process emissions for each one of those harvests. And so you can see, if you're looking at a single acre, that you're basically dealing with, through time, an accumulation of carbon in places other than in the woods. How does that compare to looking at it for old growth in the same region? This particular chart is a growth in time. Well, I'm using space for time in this case. Age is on the x-axis, and this is carbon in tons, metric tons per hectare. And what you're seeing, if you're just looking at Western Washington federal lands, so they include some old growth stands, is basically you're topping out at about 175 tons per hectare, which is bounded upper and lower by a couple of studies out of Vancouver Island for fully stocked old growth and old growth with some decay in the stands. It doesn't compare with some of the work that's been done in Oregon and the research plots that probably Mark will talk to, where they're running at about 432 tons of carbon per hectare in the above ground parts. So you're comparing above ground to above ground here. How can we address that? We're actually doing we're pretty close to that after about 100 years. We can, when you consider both what's in the forest and what's in the product stream, we're pretty close to reaching that sort of Western Washington average. But I want to take you back to this kilograms of CO2 reduced per kilogram of wood fiber for a second. If you look at, there was a meta-substitution study done a second time actually in 2011. And what they did is they looked at all these substitution studies and came up with an average value from all the studies in North America and Europe of 2.1 to 1 in terms of a carbon-to-carbon substitution. That means for every kilogram or ton of wood that you're using in place of these other products, you're displacing 2.1 tons of carbon from fossil emissions. So if you think about this substitution, you start to see that that's really the place where the story is in terms of the way that forests and forest products can offset this increasing atmospheric CO2 emissions. So if we look now back at that Western Washington commercial forests, here was our average in terms of the current forests, and here is the average from the old growth on those research plots down in Oregon. And you can see when you start to add that substitution value in there, we can still achieve that on a managed forest. Similar to what we would have had if we had, with the added benefit of having all the products that we use in our buildings. Now, looking at a single acre sometimes confuses people, so we've also looked at it at a landscape level. This is the same kind of study. This one's for Eastern Washington, Idaho, and Montana, where I went backwards 30 years and looked at what was the harvest rate, and then I implemented that harvest rate going forward on that inventory. And we actually were able to maintain, with investment, which meant you had to plant it and stand tend it, with investment, we were able to maintain sort of a stable carbon profile in that forest, in the growing stock, a little bit of an increase. And so when you added in your wood products that were pulled from it and your substitution, you could really see that that's the place where, when we're trying to offset fossil fuel emissions, that's the place to do it. Because we're fighting with a 1,000-pound gorilla, and just putting all the forests there and continuing to produce emissions from fossil fuel sources is not going to solve that problem. So some bottom line conclusions are: grow more wood, harvest it, grow it sustainably though, harvest it, use it for very high value products where you can, do some engineering, the engineered wood products are better, and when you can't, you can use those low value products for some energy sources, which I think this afternoon session is going to talk about. One of the things that really has come up in here is that essentially fossil energy is too cheap, and it's going to continue to outcompete wood in most of these processes unless we find a way to reconcile the full cost of fossil fuel use over some of the alternatives that we've presented today. And with that, I'd like to thank all of the folks that helped in producing much of this data. Thank you.
Our next speaker is Mark Harmon. He holds the prestigious Endowed Richardson's Chair for Excellence in his field in the Forest Ecosystems and Society Department at Oregon State University in Corvallis, Oregon. He is also professor of forest science. Today, Professor Harmon is going to explain some of his concerns about the current state of forests and carbon science. Professor Harmon is a leading researcher in forest ecology. He holds a PhD in botany and plant pathology from Oregon State University and a Master's of Science in Ecology from the University of Tennessee. Please welcome Professor Mark Harmon.
Thank you very much. Glad to be here. I want to address this question today, whether the forest sector is in danger of losing credibility. And I believe the answer to that is yes, but let me explain why. But before I get into that, let's talk about why that's of concern. Because when people started thinking about greenhouse gas mitigation, of course, forests were brought to the table, but there are a lot of concerns about it. There was a credibility issue. The first one dealt with the fact that forest stores are not permanent, they're dynamic. We could build up carbon in a forest, and then maybe there's an insect outbreak or a fire that might release some of that carbon. But actually, no carbon stores on Earth are permanent. They're all controlled by inputs and outputs. They're all dynamic. It's no different than any other system of carbon on Earth. The other concern was that forests are too complex, and our previous two speakers dealt with some of that complexity. True, forests are complex, but they're no more complex than technology. You can't convince me that the capture of CO2, transport, injection beneath the ground, assuring that it doesn't leak out of the ground isn't complex. The other thing that happens is this phenomenon of leakage in forests. We do something in one place and it's offset by something happening somewhere else. It's true that happens in the forest sector, but that happens in all the sectors that we're concerned about for greenhouse gas mitigation. Now let me go through a little basics. It should be pretty simple to give a sense of what I'm talking about later in the talk. And the first deals with this idea of how can we have an analogy that explains how a forest works. And so a really good one is a leaky bucket. We have carbon flowing in, we have carbon leaking out of the bucket. Comes in through photosynthesis at the top, goes out through the forest sector as a whole through respiration, combustion, leaching, and erosion. Now, inside it, we can have also some sub-buckets. And so it comes in through photosynthesis of live plants. They may die, they may be combusted in a fire, or maybe they're harvested, and so it leaks out. And they're all like that, input, output, leaky bucket. And we know if we pour more into a bucket that's leaking, it'll store more. And if we have larger holes or it's leakier, it will store less. It's really pretty simple. Now let's look at some consequences of this system. The first is, if we have this leaky bucket system I'm describing, and we have constant inputs, and it's leaking, it's going to act like the upper left diagram. It will build up its accumulation of carbon, then it will come to a balance. That's exactly what Professor Gower talked about. On the other hand, if we have a system with inputs and no losses, we have this linear increase forever of carbon. Okay, that's important. Now I want to turn to two cases in which actually we see this forever increasing amount of carbon. The first dealt with Sebastian Leissert et al.'s paper about old growth forests as carbon sinks. Basically, it states that the classic theory is wrong, that there isn't any saturation, and the forests have a net constant carbon gain. And what's important about this paper is not only it's a radical idea, but it's been cited a lot. Now, no doubt some people have been critical of this idea, but a lot of them have been used, and I've reviewed manuscripts on this that say, this proves old growth forests are going to take up carbon forever. Okay? Now let's look a little bit more at the results. I've redrawn them so they're easier to see. We have time on the x-axis and then the flux, movement in and out on the y. The upper blue line shows net primary production. That's the input to the system. That rises up and stays steady after a while. The red line on the bottom is the respiration loss. Okay, so that is negative and it's losing, but it doesn't equal the NPP. It's about half that number. So we have, through time, this net accumulation, this net positive. Now their data goes out to 800 years. I've extrapolated it to 1,000. They provided no explanation of why it would ever decrease. Let's look at the consequences of that, because that's saying we have a steady input with no losses. If we start with some reasonable amount of carbon store in that system and have a little bit of loss, the upper dark line shows the consequences for carbon stores of that finding. Now, we find a couple of interesting things. The old growth box there, PNW old growth, those are what have been inventoried in old growth forests. They're about 400 to 600 years of age. Those evidently, which are considered some of the world's highest stores, aren't high enough by about a factor of 2, according to this result. The world record is about 1,700 tons per hectare. Evidently, most forests should be reaching that level. In fact, the ones that are 800 years have actually surpassed the world record. Now, one has to ask, where are these forests? Why didn't they find those stores in the forest they measured? I have no real answers to that, but it's a very uncredible result. And actually, if we address the fact that some of the losses come through respiration, yes, that's what they accounted for, but there's leaching and erosion and other things, we could be on that lower red line and explain their results completely. They just haven't accounted for all the losses. So possible explanations. Well, there are methodological biases in both ways. We don't do a very good job of measuring soil carbon stores, but I rather doubt we're getting it off by a factor of 4 or 5. And we do know that this methodology that they used has a bias towards uptake. Maybe that's it. They don't account for all the loss terms, as I said. There's things other than respiration. Maybe they didn't observe the forest long enough to see a real long-term trend. Maybe there are recent changes that have made all forest sinks. That's all possible, but I don't think this idea that they're carbon sinks for a really long time is very feasible. Let me switch to the other end, which is product substitution. We just heard about that. And the idea is that if we could replace concrete and steel with wood products, which take less energy, we could have this very large substitution benefit shown in orange. But notice it's a linear increase. What does that tell us? There are no losses in that system. That's what it tells us. Now let's look at some of the assumptions. Some of these have been published and some not. One is that substitution is permanent. Once it occurs, it never gets degraded. No losses. Second one, there's no relationship to the use of the wood products. Now that seems a little curious since it involves wood products, but okay, that's the assumption. And the third one is that that difference, that displacement factor stays constant over time. Let's examine whether these really make sense. Let's start with the carbon costs. They actually are changing. Steel that was made 20 years ago took about twice as much energy as it does now. Concrete and steel, all those people make that, they have to pay money for that energy. It's expensive, plus their environmental costs. They're trying to reduce their energy costs. Now, whether they're as successful as in the wood products, that's another matter. In this diagram, we see through time, and then we see the wood substitution. The upper line shows a constant cost assumption. And each year, we add a little bit more into it. The other lines show what would happen. What if those costs decreased by 50% in 20 years? That's the lower blue line. The red is 200 years. See, the line starts to curve over on us. Let's do a thought experiment to explore these implications, or whether it makes sense that there's no relationship between product substitution and the products. We'll do what physicists do. We'll have a closed system, and we're going to fix the area of land that supplies the housing. We're only going to take wood from that area, and we're going to assume that the speed at which that land can produce wood is fixed. That is, we've maximized it. Now, what happens if the housing is lost before the regrowth occurs? Suppose we harvest every 50 years and we rebuild the houses for everybody, but suppose there's a catastrophe and in 25 years the houses are destroyed. Where do people live? They have to build houses out of what? They can't build them out of wood. They'd have to build them out of these other things. So that couldn't be a permanent substitution. But we could do it the other way too. What if we could wave a wand and suddenly the wood would last, instead of 50 years in houses, 100 years? Well, we could support twice as many people in those houses, right? But the assumption that there's no relationship says there's no extra substitution gain. I don't think that makes sense. And it has major consequences on how we perceive the substitution effect. Here we have the product substitution. The upper black line is the housing is permanent. It never can be destroyed, and we have a steady linear increase in the substitution. The other ones show different housing lengths. The upper red line is 200 years, next is 100, and then 50. See, the substitution benefit really is very sensitive to this assumption about the permanence and longevity of housing. Now, a very untidy fact is that if we don't use the fossil energy, someone else likely will. It's not an idea that I like, but it's a reality. Saudi Arabia is investing heavily in solar energy right now because they want to replace the use of oil to generate electricity with solar. That's because they're going to store that oil? No, that's because they're going to sell it to us. So it's not staying in the ground, folks. If we make different assumptions about how long that fossil fuel will not be used, the upper black line shows it's never used. The other lines show 25 years versus 50 versus 100. Even if it's 100 years we can delay the use, we still don't get anything close to that black line. Let's put them all together, the combined effects here. What we have here is a system in which we have an agricultural field. We've planted trees on it, and we're going to use those trees for products. We see the time since that policy was implemented on the x-axis, and the carbon that would be stored. The blue line shows what happens in the ecosystem, gains in the wood and the dead wood and in the soil, and also in the products that we create. That shows that increase. The upper black line shows what would happen if we added in substitution using those maximum assumptions of permanence and no relationship whatsoever to the products. Okay, big gain, and it's going to go up forever. However, if we make some realistic assumptions that houses last 200 years, that it takes 100 years for that carbon that we try to prevent coming out of the ground to leak out, that we basically reduce the carbon cost of concrete and steel by 50% over a 100-year period, or actually a 200-year period. Those are pretty conservative assumptions. We get the red dashed line. We see the product substitution virtually adds nothing to the storage of the system. Now let's look at it again at some other starting conditions. Suppose we have a pre-existing system that has been producing buildings. That's on the left. Well, with the assumptions of permanent offsets, substitution that has no relationship to buildings, we get the black line. If we make realistic assumptions, we have no gain in the system whatsoever. On the right shows an old growth conversion. We take an old growth forest and we convert it. Again, with the maximum substitution assumptions, we have this major gain. When we actually deal with realistic assumptions about housing use and longevity and leakage of fossil fuels, we get the red line. We actually have a loss of carbon in that system. So my concern is the following. What are those outside the forest sector to conclude? Because whether the forest sector participates or not in mitigation isn't up to the forest sector. It's up to the people outside of it and whether they trust it. Okay, so both sides are right. Let's assume they're both right. Well, then the forest sector is irrelevant, isn't it? Because no matter what we do, the forest sector is going to take up a lot of carbon. So why even worry about it? Well, what if they're both wrong? Well, I think people outside are going to say, you know, this forest sector science is pretty weak and untrustworthy. And what if one side is wrong? Well, my conclusion is that one side's engaging in largely a PR exercise and not really in science. So you can decide who's right and wrong. My point is that regardless of how this turns out, it's not good for the forest sector in terms of credibility. Now, you may take it to mean, this talk to mean that I don't think the forest sector has the role to play. Actually, I think it does have a role to play as a potential in mitigating greenhouse gases. But to play this role, the science has got to be credible. And the policy that comes out of that science has got to be credible. And my major point is the track record of the forest sector right now is pretty checkered. And this needs to change as soon as possible if we really want to participate in what needs to happen. We all agree has to happen. We have to mitigate greenhouse gases. With that, I'll conclude my talk and thank you once again.